I approached Harvard and MIT students and asked them to explain wave-particle duality in quantum mechanics. Their unscripted answers are presented. In this video, I first provide the explanation. By the end, you will understand the perplexing concept of wave-particle duality and find yourself even more enthralled by the wonders of physics. Do you understand wave-particle duality? Okay, here's the question. What is wave-particle duality in quantum mechanics? A lot of people have heard about the ideas of wave-particle duality in quantum mechanics, but it's confusing. It's not intuitive, and I think most people don't really understand it. I'm going to begin by explaining wave-particle duality. You may want to pause the video right now and answer the question, what is wave-particle duality? Light behaves as a particle when it is being emitted by an atom or absorbed by a detector. There are many different types of detectors. For this presentation, we'll be discussing photographic film. When light is being detected, it behaves as a particle. That is the particle nature of light. Light behaves as a wave while it's traveling from the source to the place where it's being detected. Light strikes the detector as a particle, but it travels to the detector as a wave. This slide's a demonstration of how light is detected as particles. Photographs consist of discrete points, each representing the impact of a photon on the photographic film. This is especially noticeable in low light. If you look at these series of photographs, the one on the far right, it might not be obvious that this is made up of many discrete specks or points of light. In low exposure, that's much more obvious. And so what's happening is the light is incident on the photographic film, and once the light hits the film, an individual photon of light excites one of the atoms, then there's a chemical reaction and you get a small speck. You get a spot of color where the photon or particle of light hit. I want to remind you of an important property of waves. Waves are the only object in physics that can interfere with each other. On this slide of an example of constructive interference. Constructive interference is when waves interfere constructively with each other and they reinforce each other. And this is an example of constructive interference of waves. Waves can also interfere destructively, and on this slide, I have an example of destructive interference of waves. And this is when waves interfere destructively with each other, they cancel each other out. Waves are the only things that interfere in physics. On this slide, I'd like to explain Young's double slit experiment. This was an experiment done by Thomas Young in the early 1800s to prove that light was a wave. Light was incident on a barrier. This is the barrier, this is the light coming in, and the barrier had two slits in it. When light is incident on a barrier with two slits, the size of the slits are on the order of the wavelength of the light, then the light will diffract when it leaves the slits. And what that means is the light comes out in these spherical wavefronts. You have two spherical waves coming out of the two slits. And because waves interfere with each other, what you get is what is known as a double slit diffraction pattern or an interference pattern of the waves from the two slits. The way this works is there's going to be a central maximum and then a first order dark spot, then a first order bright spot, and then a second order dark spot, and then a second order bright spot, and so on. And you get these alternating spots of these alternating lines of dark and bright. And this comes from interference of the waves. Any phenomenon producing diffraction pattern must be a wave. This is proof that light is a wave. And this is an example of an interference pattern. And this is the way light behaves. This is the way any wave behaves. If you had water waves going through the slits, the water waves would also form an interference pattern. Any waves, not just light, any waves form an interference pattern. This is a simulation from the University of Colorado. And if we have light leaving in these spherical wavefronts of light interfere with each other, and you get an interference pattern. This is the Young's double slit diffraction pattern, and you get these intensity peaks. If you're finding education or entertainment value from this content, please like and subscribe to my channel. Also, check out my website, acephysics.org, for math and physics tutoring. Now I'm going to explain what it means for particles to form an interference pattern. This is the barrier with two slits. And imagine that we're sending a whole bunch of particles in. Photons hit the screen at discrete points. They avoid areas of destructive interference. Maximum impact occurs in regions of constructive interference. When there is total destructive interference, particles never hit the screen at that location. What determines where an individual photon hits the screen? Interference determines it. So imagine that you're sending photons through a double slit, and to the right, there is a screen where the photons are hitting. These pictures on the right show photons hitting the screen, and exposure time is getting larger as you move from the top of the screen downward. For low exposure time, there are many little spots where the photons hit. Each one of these hits one photon at a time. But you can see as the exposure time gets really, really large, there are locations, there are these lines where the photons never ever hit. And that's because these are locations of destructive interference. Even though the photons hit as little discrete particles, those particles know, they somehow understand never to hit in these locations or these locations or these locations. And the reasons they never hit there are because of the wave nature of light. The particle nature of light is when the photons are detected, but the wave nature of light says you can never hit at a location of destructive interference. On this slide, I want to show what would happen if large-sized particles like tennis balls were incident onto a barrier with two slits in it, and then there was a wall. So this black line is a wall, and then here is a barrier, slit 1, barrier, slit 2, barrier. The tennis balls are being shot through. Some of them would ricochet off the barriers, but some of the tennis balls would go through slit 1 and slit 2. And this is the pattern you'd get. You'd get most of the tennis balls would go right through the center of slit 1. Some would ricochet off the walls and go over here, and some would ricochet and go over here, but most of them would be in front of slit 1, and the ones that went through slit 2, most of the tennis balls would be right in the center of slit 2. You'd get two stripes, two intensity patterns. It would not be the case where there'd be many tennis balls would hit here, no tennis balls would hit here. Many tennis balls would hit here, no tennis balls would hit here. That's not possible classically. This slide shows you what would happen classically is you would get two stripes. What would happen based on the wave particle of nature is you'd get all these discrete lines. If light, which is a wave, can behave like particles, can particles behave like waves? Louis de Broglie, a French physicist, proposed the idea of wave-particle duality in 1924. And as it turns out, particles can behave as waves. Evidence for the wave property of matter is interference of matter waves. Examples of this are electron diffraction, neutron diffraction. There's also been diffraction of helium atoms and C60 molecules. Electron diffraction happens all the time, and this is the working principle for electron microscopes. Electron microscopes rely on the wave nature of particles. They rely on the wave nature of the electron. I went to ResearchGate and I found a paper by Herman Batlian. This was a 2015 paper. Here's the title of the paper, and I'd like to show the data on the next slide. Recently, we performed the electron double slit experiment, and the pattern was recorded one electron at a time. The electron detection rate was about 1 per second. This made it possible to manually turn off the electron source after the first electron was recorded. 1 per second. One electron goes in, wait a second. The second electron goes in, wait a second. And the exposure time goes from the least at A to the most at E, and you can see at E they get a diffraction pattern. Get a diffraction pattern for electrons, but the electrons are particles, they're not waves. However, particles can behave as waves, and this shows that. Individual electrons are incident on the double slit. The individual electrons have wave properties, which means that they go through both slits. If you sent a wave into two slits, the wave would go through both slits and interfere with itself. So in this case, the individual electron is a wave. That wave goes through both slits. It interferes with itself, produces an interference pattern, and then the single electron is detected at a location on the screen where the interference pattern is a maximum. This is the data, and as you notice, the electrons are detected where you have these light spots, and there's these dark spots in between the bright spots where the electrons are never detected. And this is an example of the wave nature of matter. I'm standing in front of the statue of John Harvard.
Alex?
And you're a postdoc here at
I'm
MIT?
a postdoc here.
And you did a PhD at Berkeley?
Correct.
What was your PhD on?
Theoretical condensed matter physics.
Okay.
Well, it just speaks to the nature of how complicated and intuitive quantum mechanics is.
It's a great answer. When did you know when like waves like a particle?
Yeah, like if you do the double slit experiment, it shows like it's a particle. No, I think that shows it's like a wave, right? Double slit shows it's like a wave because you get a diffraction pattern there. but I think it's a particle. Yeah, I think intuitively think it's like a particle, but I know that double-slit experiment is like famous one where it shows like it's a wave.
I can explain it badly, but I think that bad explanations are largely what exists for it. So my personal take is that it is sort of inaccurate to say that sometimes, so these objects are called quantons. Everything can be described as a quanton, but if it's very big, it ceases to be useful to describe it in this way. But quantons are objects that sometimes behave like waves and sometimes behave like particles. And from where I sit, it is inaccurate to say that they become waves or become particles, depending on the context. They are their own things. When you observe a quanton, which is to say when you interact with it in some way, its properties take on specific values. That means that its angular momentum might be a specific thing, its position might be a specific thing, its velocity might be, its linear momentum might be a specific thing. But when particles are not being interacted with in the specific way of measurement, they propagate through space and time instead of as sort of a particle, like a ballistic, a ball that's just moving. They propagate through space and time as a probability distribution. Technically, they propagate as a probability amplitude, and you have to do some math to it to get the probability distribution out of it. But the idea is that they don't behave deterministically, which is to say, if you have a ball and you throw it, you can if you know how hard you threw it, you can close your eyes and know exactly where it's going to land. If you throw an electron, none of that is true. All of a sudden, as soon as it leaves your hand, it starts to have an indeterminate momentum and position. And instead of saying where it is going to go, all you can say is where it is likely to go and what the probabilities are of it being in any particular place at a particular time with a particular speed.
Oh, okay. I'm trying to remember. Isn't that like the slit experiment?
That is an example.
It's like light is a wave and a particle at the same time.
Uh-huh.
And it's like when you try to observe which one it is, sometimes you can't tell. Or to like, I haven't thought about the slit experiment since sophomore year.
Okay. That's okay. That's
It's like
okay.
you put it through the interface, the slits, and then it comes out. You shoot it as a particle and it comes out as a wave, right?
You shoot it as a wave and it's detected as a particle.
Oh, okay.
Yeah.
Okay.
Okay.
Right,
Oh, great. Can you explain, what do you know about wave-particle duality?
I think it's like the double slit experiment where they found out that the light was destructively interfering, right? So that's why it only would show up in like discrete positions. So that was proof that it was actually a wave, but also can be modeled as a particle as well. And I forget how they knew it was a particle, but I know that double
It
slit.
has to do with the fact that they are orthogonal to each other.
What's orthogonal?
Oh, they are, right?
Like light versus electromagnetic. Well, that is light. Forget what the other one was.
Okay.
The mathematical object that we can model particles with is, well, at least in classical quantum mechanics, is like the wave function. Now the wave function can be very localized. This is an eigenvector of like the position operator, which is if you were to multiply your wave function by x space, then like the only things that are truly scaled by that are just like functions that are some number at just x and 0 everywhere else. And so this is kind of like, I think, what a particle is, where it's very localized. On the other hand, like if you do a different operation on the wave function, which is you take the derivative, you like multiply it by I or something, then like the shape that would be scaled by this derivative, so like the intersection between like scaling and differentiation, there's a function there which looks like a corkscrew, and this is like a wave, and that operation is called the momentum operator. So things that have a well-defined momentum have to be in a corkscrew shape, and things that have a very well-defined position need to be in like a spike shape. But particles have both position and momentum, at least as within some uncertainty. So They have both like the wave properties and the particle properties. At least that's how I tend to understand it.
Have you ever heard of wave-particle duality in quantum mechanics?
No.
Okay.
Wave.
Particle duality. Quantum mechanics, where something can be a wave and a particle. Sometimes a particle is a wave.
Yes, that's from Einstein, right? From Einstein. Not from. Oh, Einstein is not.
Einstein's relativity.
Yeah, Einstein is not quantum people.
Yeah.
Yeah, I heard about that because the light can be particle and wave at the same time.
Yes.
Yeah.
What is my question is just, what do you know about that? It's a very complicated topic.
Yes,
so
yes.
what is your understanding? That's your understanding, is just that light can be a particle and a
Yes,
wave?
yes.
Okay. Have you ever heard an experiment where maybe anything is done with that?
Yes, and I remember from the physics class they have an experiment. The light can go through the double split and then generate a circle, the ring.
Mm-hmm.
Yeah,
Yes.
that's called. I'm not good at explaining it in English, you know.
A double slit interference pattern. That is a good example. All right, so maybe here's a harder one.
Oh, I remember the name. Something Yang experiment.
Yes.
Right? Yes.
Perfect. Yes. A+. You got it.
I'm Naomi Gendler. I'm a postdoc here at Harvard.
And what do you study?
I study string theory.
Okay, just out of curiosity, where did you do your PhD?
I did my PhD at Cornell.
Can you explain wave-particle duality in quantum mechanics? Like, what does that mean? Do you have any understanding of what wave-particle duality is?
Yeah, it just means that every object has a wavelength associated to it, and so okay. Well, let me think of a good explanation. Yeah. What I would say is that every object has a wavelength associated to it. So every object, even macroscopic objects, are in some sense a wave and a particle. But for really macroscopic objects, that wavelength is so tiny that it doesn't matter. But for really tiny objects, like an electron or something, that electron would have a large wavelength, and practically speaking, what that means is that if you have a bunch of tiny particles and you do stuff with them, they can interfere with each other like waves, but they can also move like particles.
Perfect.
Shira?
And I assume you're a student here?
Yeah, no, actually, I'm a visitor. I'm from USC.
To USC?
Yeah.
What do you study? What are you a grad student?
Yeah, I'm a grad student.
Okay.
I'm studying interactive media.
Okay. Oh,
Yeah.
that's a little removed from physics, actually. Have you ever heard of the wave-particle duality? Wave-particle duality in quantum mechanics?
I'm not sure. Can
Okay.
you explain more on that?
Sometimes particles behave like a wave, and sometimes they behave like a particle. And it's kind of like a fundamental thing in quantum mechanics that some people might have heard of. That's something maybe you haven't heard of. Okay.
Yeah.
I'm Yi Chen.
And where are you from?
I'm from China.
And what do you study?
Chemistry.
Chemistry?
Yes.
What year are you?
I'm a second year grad student.
Well, there's something called the wave-particle duality. Have you heard of that?
Oh yeah.
Just what do you understand about the
Oh,
wave-particle
let
duality?
me give you an example. So there was like a debate on it, like thread light on to like metal, you might excite electrons from it. And sorry, I forgot the name of that.
The photoelectric effect?
Yeah.
So when the light hits the metal, one single electron comes out.
Yes.
One single electron comes
Yes.
out? Yeah.
Yes,
Okay.
so that means it looks like you got a particle in it, and it hits to the metal, and you an electron goes out, and that shows like light is like a particle.
Okay.
But they can like, but it also looks like a wave, so you can do like.
That is great. What you just said was really great.
Yes, and
it was
that's
good. It's very
that's
good,
from
really
light.
great. Yeah.
But then people find like electrons that they'll also behave somewhat like a wave, and that's and then there's.
So you just said how waves can behave like a particle.
Yes.
When can an electron behave like a wave?
Like you can do so you can do diffraction. Yes.
Very good.
Yeah.
Great. Below is a list of fundamental experiments in quantum mechanics that are essential to understand if you want to understand quantum mechanics. The first experiment is the double slit experiment. I've explained that already in this presentation. Hopefully the ideas are more clear to you now. Other experiments that are crucial in quantum mechanics are black body radiation, the photoelectric effect, the hydrogen spectrum and the Bohr model of the atom, the Stern-Gerlach experiment, Compton scattering, and then two more advanced experiments, two other experiments that require a more advanced mathematical understanding of quantum mechanics are the transistor and band gaps in material, as well as superconductivity. Light is a wave when it is traveling through space, and it turns into a particle when it is detected. Fact. The energy of a particle wave or of a particle of light is equal to h times f, where h is Planck's constant and f is the frequency. The relationship here is not classically intuitive. In classical physics, the energy of a wave is related to the wave's amplitude, not to its frequency. On the quantum scale, energy comes in small chunks. Nothing is continuous. As of 2024, quantum mechanics is used to describe atoms and subatomic particles and things that are small. And the reason that this is the case is because wavelength of matter is equal to h over mv. H is Planck's constant, and if m is a macroscopic mass, if it's like your mass or the mass of a car or the mass of a building, it's so large that the wavelength is negligible. The wavelength is tiny. And if the wavelength is tiny, the wave nature of matter is insignificant. And so for this reason, macroscopic objects are not described by quantum mechanics as of 2024. Because particles can behave as waves, there's a wave equation for particles, and this is called the Schrödinger equation. I've written it up here. This is an equation for waves, and it tells you the wave nature of particles.